Okay, so I'm going to ask you to use your imagination today, probably much more than the other talks, because I'm not really talking about lessons learned, but really more about functionality that I'd like to be able to enable in the future. So initially, I was going to ask you to use your imagination and imagine that I was going to be giving out €100 at the end of this talk. But since we have Dashlane actually doing a lottery today and giving out an Apple Watch, I don't even have to ask you, I don't even have to pretend that I'm going to be giving anything to you. But I would like you to imagine, hypothetically, that Dashlane is an evil company and that you don't trust them to actually pick somebody to win the watch in a fair way. Maybe they want to pick somebody who's actually their own employee. Maybe they want to pick somebody who they've already made a deal with to give the watch back. Maybe the watch doesn't even exist. So you could ask, how could Dashlane prove to you that they're actually running an honest lottery, that they're actually really picking somebody randomly from amongst all the people who are in the audience here today to win that Apple Watch in about an hour when they do the drawing? So what you might think about, the technology that's been around for a really long time, is to try to generate some randomness physically. So this is obviously really ancient technology. It exists in most cultures in different forms, rolling dice, casting lots. There's a lot of ancient references. And that's kind of the first thing that we'd think of, and I think we actually might see some version of that later today. I can say I was not involved, so I didn't set up the lottery, so if it's rigged, don't blame me. But they might do something like having a bowl with everybody's name in it and picking a name out. That might look okay, but already there's a couple of gaps there. You're not really sure that everybody's name is in the bowl. You're not really sure that they're picking fairly. But you can imagine that's probably what would be done. That's kind of the standard thing that you'd expect. So let's think about how we could strengthen that a little bit, assuming that, like we have today, we have an audience full of developers, specifically developers who are interested in security. So the first thing that I would do if I was running the lottery is I would commit to the algorithm. And it could be very simple, but notice that committing to the algorithm, I'm going to have to commit to the set of names, which would at least prevent some basic attacks, like putting hundreds and hundreds of fake names into the bowl to try and rig the odds. So we want to have some time period where the algorithm is committed to and everybody can look at it. So everybody can make sure that this is correct, that it's actually implementing a fair lottery, that if they signed up, that their name is actually included, and so on and so forth. Then after we've committed to what we're going to do and had given everybody a chance to look it over, we're going to need to pick a random seed. So that program is obviously going to call some random number generator somewhere since it's a lottery. So we're going to have to input a random seed to make that work. And maybe we'll have some isolated physical randomness process for that. So maybe we'll just come up and roll a couple of dice, generate a short random string, expand it if we need to using a pseudo-random number generator, and then we can run that algorithm and it will produce some result. So we'll run the algorithm given that seed. And then the beauty of this process is that anybody should be able to run it themselves and check that they get the same result. And if you don't get the same result, what do you do when developers are unhappy about something? Probably complain on Twitter and hope that that somehow leads to the world being made whole. So I would argue that essentially every step here is pretty sound and we understand pretty well, except that third step there, generating the seed. And we're pretty limited as to what we can achieve security-wise by doing some physical random display. If you've ever seen a magic show, I mean, this actually certainly feels like a venue where you could have a really good magic show. You know that magicians can do pretty incredible sleight of hand. So it should be no trouble for a professional magician to roll some dice and get exactly a number that they're expecting to get, or to pick exactly the name out of the hat that they want. So I'm going to pretty much just dismiss the fact that we can ever make the physical randomness type of draws actually verifiable. Certainly not if some of the participants are remote, where you have to actually watch it on video. Then you get into the world of Hollywood and special effects. And if you don't believe me, there's a really rich literature from lotteries that have real money involved of how people have actually rigged these things. So much that Hollywood actually did make a movie starring Phoebe from Friends, that showed how they rigged a lottery in Pennsylvania in the 1980s. And the way they did this one was really simple. They actually just put lead weights in the ping pong balls that they wanted to come out of the lottery machine, so the heavy ones sank right to the bottom. And there's also some examples of lotteries that have failed not because anybody was actively cheating, but just because physical randomness, it can be hard to estimate how much entropy you're actually generating and to see that you're actually getting good uniform randomness. We do have technical tools that can take even a biased non-uniform random source and output uniform randomness, but you do need to know something about the min entropy of the source, and that can actually be hard to estimate for these physical sources. So the example here, this was a famous lottery that happened in the United States to determine who was going to be drafted to fight in the Vietnam War. And they mixed the thing on the wrong axis, so the balls didn't actually mix. And the results, when they actually plotted it, they got some mixing to happen, but generally the balls came out in the order that they went in, and they put them in order. And when they ran statistical tests, they could tell right away that they had kind of botched this, and it led to an unfair lottery. So what we'd like is to imagine some perfect service. This is where we get to use our imagination that would just sort of solve this problem for us. So this is what cryptographers do a lot. They sort of imagine some perfect object that you could build really great security systems out of, and then they argue for years and years about how to actually do it. So we'll get to that in a second. But the imagination part is to imagine this object that cryptographers call a randomness beacon. So what is it? It's this object that just constantly outputs a stream of uniform random bits with a bunch of great security properties. So nobody can predict them. There's no party in the world that knows what it's going to output next. Everybody sees the same value. We have unanimous consent. This thing's reliable. It never goes down. And it's high bandwidth, so it's always on. It's always outputting lots and lots of randomness. So you can imagine that if this object existed, our lottery process would be pretty easy. We would commit to the algorithm, and we just say, at a certain point in time in the future, we're going to sample from the randomness beacon and run our algorithm based on that. There is a fifth property that we would like this imaginary object to have that maybe I'll circle back to at the end. But we'd like to actually be able to convince the public that this thing exists and that it's really behaving as advertised. So this is a much, much harder property, but it is kind of there lurking in the background. Okay, so what are some attempts to do this? Well, if you want to just trust some third party to do this for you, this is always kind of step zero in cryptographic design, is just say there's somebody that everybody trusts, and then usually problems are pretty easy. So there's commercial services that do this, like random.org. The US government does it. NIST, the National Institute of Standards, runs a beacon. But of course, these are really only secure if you trust that that party is operating this beacon correctly. Otherwise, they're fantastic engineering-wise. They output tons and tons of randomness. They update constantly. And statistically, at least, the randomness looks pretty good. You know, whether or not it's actually honest, I can't really tell you because it's not verifiable. So philosophically, what we'd like to do is drive our beacon, generate our randomness off of some big physical process that we're convinced that human beings don't have the ability to control. The sun would be really great. The sun is really big. The sun is doing random stuff on its surface all the time. And I'd like to believe that Dashlane is not going to be manipulating the surface of the sun to control who gets the Apple Watch. And there's really great websites that monitor the sun all the time. There's a big hobbyist community, so there's tons and tons of data. There's a lot of entropy in what's happening on the sun, and you can extract it all. The problem with this, if you look at the bottom of the screen there, where do you actually get this data from? Well, there's actually a government observatory that publishes this data of what's happening on the sun. And it could be that you don't agree with their observation. You could also be looking at the sun and say, that's not exactly what I see, and you end up needing a trusted observer to decide which value you go with, and we've sort of reinvented our trusted observer problem. So while this would sort of be the ultimate in terms of security and unpredictability, it doesn't have that unanimity property. We're not guaranteed it's easy to come to consensus about the value. So I'd argue, taking a step back, that this is why we sort of need cryptography to solve the problem. So a lot of people think about cryptography as secret writing or just keeping things secret, maybe also doing some authenticity. But when I teach cryptography to students, I usually say that what we're really trying to do across a whole range of scenarios is replace some trust assumption with a computational assumption. So rather than having to trust some entity to behave correctly, we just want to trust that some mathematical problem is hard to solve. And I'll talk about how we can try and replace trusting some entity like NIST or random.org with some computational assumptions. And now it's time for me to start talking about blockchains. So if you had the over-under at halfway through my talk before I started talking about blockchains, that's where we are. So the observation is that blockchains, like the Bitcoin blockchain, but also all of the other competitors to Bitcoin, are really, really close already to being this perfect beacon service. So they update all the time. It's really hard to predict what the next block is going to be. It takes input from lots and lots of people using the system from all over the world. And it also has this sort of magic proof of work property, which guarantees that they're hard to predict. And it gives you consensus basically for free. That's the whole point of blockchains, is that there's this distributed consensus algorithm, so everybody should agree on the values. So essentially, we get all the properties we want for free with a question on the unpredictability part. So in one sense, it's hard to predict because it's very, very hard to find blocks in the Bitcoin blockchain. As you may know, there are really big entities running factories in Western China and exotic places, running tons and tons of chips all day and all night long, trying to find blocks. So if it was easy to predict what the next block would be, they wouldn't be out there burning hundreds of megawatts of power trying to find it. So we have some pretty good confidence that it's hard to predict exactly what the next block is going to be. The only trouble is that blockchains, as you know, are subject to forks, or as we like to say, reorganizations. So there are cases where there are two potential blocks that are found around the same time, and it's not clear which one will ultimately be part of the blockchain. And think now that if we're running some high-stakes lottery off of this blockchain, it might really matter now which of these two blocks ultimately gets selected to be part of the blockchain. And we don't really know for a while, so the system can kind of be in an unsettled state for a short period of time. But there's kind of an assumption that eventually the network will always converge on one unanimous version of the blockchain, or one longest chain. So this is a conjecture that Bitcoin researchers are working really hard to prove, and we're not quite there yet, that having some long reorganization is an exponentially unlikely event. So essentially, if some block is followed up by a large number of blocks, with very, very high confidence, you can say it won't be overwritten at that point. It's in the blockchain permanently. So here's the one cryptographic trick that I'm going to introduce today. That will show you how we can make this blockchain construction much, much stronger, which is to add a new cryptographic construction that I call a delay function. And the goal is to make it hard to manipulate this thing. So the idea here is that when we see these two blocks appear, we can't immediately tell what the outcome of the lottery will be. What we can do is start computing this delay function. But you can probably guess by the name delay, it's going to take a long time to actually compute this thing. And the goal is that by the time we can actually compute what the output of the beacon is going to be, the network will have already long since moved on, and it's too late to make any changes at that point. So the delay function basically buys you this property that you don't know which block you actually want, what the impact will be on your beacon, until a long time in the future. And remember that conjecture on the last screen that I showed you. We assume that the blockchain will never have an arbitrarily long reorganization. So if you buy that conjecture, it would be really great if we could prove it. But for now, it's kind of a widely believed conjecture. Then this is a great way to generate a lottery. So how could we build that delay function? I can really just show you two ideas. One, just to show you, to hopefully convince you that you can do it. You can just take any one-way function, a standard cryptographic hash function is great, and you can iterate it a bunch of times. So if you took, say, SHA-256, which is still considered a good hash function, did it a billion times or a trillion times, we'd have pretty high confidence that that's a function that takes a long time to calculate. And what's really neat is that there are actually better things you can build cryptographically. So there are asymmetric delay functions which take a long time to compute, but a relatively short time to actually verify. And I'll just show you one construction that we've actually known about for 25 years now, but it's kind of only recently that we've thought about using it to make a lottery secure in this way. And that construction is finding a square root mod p. So if you don't know the number theory and the modular arithmetic off the top of your head, I'll just show you. It's extremely fast. It's basically one line of code to compute a square root. You just raise this thing to the right power, and that gives you square root mod p. And you can do this for any integer mod p. And the nice thing is that to verify that you've actually found the square root, so if someone gives you the answer that they've computed using this slow sequential exponentiation, you just have to square the thing to see that it actually is the square root. So that was kind of the cool trick that we wanted to pull off, a slow function that has to be done sequentially, but has kind of a shortcut once you've actually found it to prove that the answer is correct. So it turns out this is kind of a rare beast mathematically. We know maybe 2 or 3 other constructions, but it's pretty cool. So I'll just pause for a second to admire. It always kind of blows my mind, just like the first time seeing how RSA works or how Diffie-Hellman works, what cool math tricks cryptographers can play to give you this functionality that maybe doesn't seem possible when you first think about it. So people are already really excited about using randomness from blockchains for smart contracts in the Ethereum world. There are already services that do it, and they're getting kind of closer to this world where they actually publish their code, so the algorithm's public, the random seed is public, and you can trust, in this case, that this casino is supposed to be honest. So what I really like about this, even though this is kind of a fledgling startup Ethereum casino, they're taking steps to try to prove to their users that the randomness is actually being generated honestly. And by the way, if you hear the word blockchain and you tune out and you think that it's all sort of a fairy tale, you can do basically this exact same construction using the stock market. So you don't have to use the blockchain at all. You can sort of observe that daily stock quotes are sort of like an old school version of a blockchain. And you can generate your random numbers that way. So you can say we're going to take all of the stock prices from the end of the day, run them through a delay function, which in this case will give you some security against high frequency traders. And that will be the output. So there's a whole lot of applications for verifiable lotteries. It's not just gambling and games. It's really big, important things like visas that are given out randomly in the US, picking people for security screening, or picking people to be kicked off a plane or reaccommodated, as we say. Things like doing audits after elections. And even just kind of maybe more fun stuff like picking the groups in the World Cup, which is something that FIFA does every 4 years. And the reason I like that example a lot is that that's one of the few places where the fans are already really suspicious of the process because they don't trust the entity doing the lottery. So this is still kind of early. It's going to take a lot of new reasoning to get this right. We have to reason about adversaries who are trying to speed up some function, possibly using really fancy hardware, possibly using a lot of parallelism. Not something that cryptographers have a lot of experience reasoning about. So I think this is going to be a fun research topic over the next 5-10 years for the crypto community. But in the short term, the message that I'd really like to leave you with and that I'd like to get out there is that it's healthy for everybody to ask authorities for verification, whether it's Dashlane or whether it's FIFA or whether it's your national government. If they're running a lottery, this is something that we should demand that they actually provide some proof that they're doing it correctly, because this is something that cryptography has the capability to deliver. We just need people to actually ask that people start to do this. Thanks.